Well then, good afternoon and welcome to our presentation. My name is Florian Eibl. I'm with Aconity 3D and I'm here today to show you a bit of the work we've been doing together with a team of Aconity, Flow Science, nLIGHT and Optoprim on a topic what we currently call 4D printing. And I want to do so by first of all defining what that fourth dimension actually is and then show you a bit of experimental results, what we can do with it. And at the end, I invite you to a discussion to find some practical applications that we cannot think of right now. So, first of all, most of you here are familiar with the concept of 3D printing. In laser powder bed fusion, we do so by melting a powder layer with a focused laser beam. And by that, we can define our future part in the first, second, and third dimension. But those of you who have already worked with laser powder bed fusion will probably know that it's by far not an easy process. So what happens is when we hit the powder bed with a laser beam, that this radiation is absorbed and then the temperature field evolves. The material undergoes at least one phase change and then there is a complex flow field with surface tension gradients, even chemical gradients, which all interact with each other and at the end define the melt pool dimensions as well as the solidification conditions. And those two, in the end, define the properties of the laser part, or in more generally speaking, the part quality. And so far, both machine manufacturers and machine operators alike were kind of limited in what they can do to influence that complex process. And as you might have already guessed from the title and the advertising, today we want to focus on one aspect of what we can do to actually take more control over the process. So the concept of beam shaping has been around probably since lasers exist. What is new in this case is that the beam shaping now takes place within the laser beam source itself. That means we can think of it as more or less two lasers in one, with an inner core and an outer ring where we can adapt the amount of laser power that goes into each other and then is applied to the process. And so we can do so generally create a Gaussian beam seen on the left side or something like a ring mode intensity distribution seen on the complete right and 5 steps in between. And since this all happens within the laser beam source within around few 10 milliseconds, it allows us to treat the intensity distribution as a process parameter similar to laser power, scan speed, spot diameter, modulation, and so on. So now, what can we do with it? As a first step in any kind of process development is a parameter study. So we want to try out where those intensity distribution can lead us, and we did so by taking our largest system, the Aconity 1, and place 180 cubic samples of Inconel 718 onto that platform and vary laser power and scanning speed in a large range, but also vary hedge distance and layer thickness. And in order to enable a more concrete comparison between the standard intensity distribution and the ring mode, we defocused the Gaussian beam so that the outer diameter is similar to what the ring mode provides. So we have no influence of significantly different spot diameters in that. And with that parameter study, we generate processing windows for each and every case, where we can then select specific parameter sets for an evaluation of the mechanical properties. And then, as you might expect, we find some differences there. And those differences are then investigated in more detail by a metallographic study. And the overall objective of this study is to find out how we can influence the mechanical properties of a laser part by varying the intensity distribution. So on the left-hand side, I don't know if it can be seen from behind, but you see the processing window drawn over laser power and scanning speed. And for that, we categorized the final samples into 3 different groups. The first group is parts that cannot be built up in a stable manner. That means we have to abort the process or take them out in order to not damage the complete build. The second group consists of parts that can be built up in a stable manner but do not achieve full density. And at the end, we have the stable builds that achieve a porosity of less than 0.5%. And what you can see is that the ring mode intensity distribution on the right, first of all, opens up a wider process window in an area with increased energy input on the bottom right. And that encouraged us to see what happens at the opposite end. So if we decrease the energy input by using higher scanning speeds. And while this was only a first shot, as you can see on the top right, it was also possible to produce stable parts in that region. And now what we then did was we selected one parameter set right in the middle of both processing windows to compare the mechanical properties. And this is shown here. For tensile samples with vertical orientation, so the tensile direction is identical to the build direction. And we now can see that we see a strange effect. We see that not only the tensile strength increases, but so does the elongation. And typically, this is something where you have to decide for one or the other. And also interesting is that we achieve as-built mechanical properties with the ring mode intensity distribution that we are used to from the standard single mode process with significantly smaller spots. But this allows us then to have the same properties at significantly greater melting rates of, in that case, more than 9 cubic millimeters per second. But the question remains, why does it happen? So the first step that we did was to look at etched micrographs. So there's a lot of small images here, but as you can see, there is no significant difference that directly hits your eye. So even for different intensity distributions and different parameter sets, the macroscopic structure looks pretty similar. So in order to dive a bit deeper, we then looked at aspects like primary dendrite arm spacing or the segregation behavior, which are also known to affect the mechanical properties. But we didn't see any suspicious things there as well. Last but not least, if we then do an EBSD analysis of the grain orientation and the texture, we finally see the significant difference that helps us explain the differences in mechanical properties. So on the left side, you can see that the orientation of the grains is very distributed for the defocused Gaussian distribution, whereas for the ring mode, we have a very sharp texture, meaning that the grains are orientated parallel to the build direction. And since this was also the direction where we did our tensile tests, that helps us explain how we can, where those differences come from. But we still don't know why this happens. And we want to know that because if we understand this mechanism, we can influence it any further. So one explanatory approach that we came up with is that we look at the melt pool shape in general. So what you see is that the aspect ratio of those melting tracks significantly differs between the Gaussian intensity distribution and the ring mode and also the one in between that. And to understand that, let me quickly explain how the solidification works. So typically, the dendrites during solidification, they grow perpendicular to the melt pool boundary, meaning if you have a great amount of curvature, the dendrites grow into each other, which leads to that chaotic distribution, whereas for a shallow but wide melt pool, we have a great number of dendrites that grow parallel to the build direction. And due to that effect, we can force the grains to grow into the direction that we want, in that case, in the build direction. And we can also back that up with some simulation results carried out by Flow Science with Flow 3D. So those simulations are actually matched to the melting tracks that we saw earlier. And the small vectors that are plotted in the top show the direction of the thermal gradient. And also in that case, we can clearly see that we have a large amount of parallel vectors, meaning a directed thermal gradient during the solidification. But there's actually a bit more going on, which was revealed by the simulation. In this chart, the vectors are the flow field or the velocity field of the melt pool dynamics. So as you can see on the left, for the standard Gaussian distribution, we have a great amount of flow behind the actual melting, the actually irradiated area. So you can think of it like the water behind a motorboat. So everything is flowing in one direction and kind of colliding. Whereas on the right-hand side, we see that the flow is more within the irradiated area, but not behind it. And if you remember the processing window from the beginning, we saw that the stability of the process was increased even at greater energy input. And one reason for that can be that you have less amount of chaotic flow within the melt pool, since you have no overheating in the center of the irradiated area. And this is also the area where the heat flows by nature. So to draw an interim conclusion, by 4D printing, we mean that we deliberately manipulate the solidification conditions in order to tune the mechanical properties towards our application. And of course, this also opens up new possibilities in terms of high temperature properties like creep resistance, for example. And since it's a parameter like any other parameter currently, we can do so not only from chop to chop, but even within a single layer, or use several different processing strategies within a single part. But of course, we are not at the end of our work. So one very important aspect in that regard is that we look at the anisotropy of the mechanical properties, because of course it can be different perpendicular to the build direction. But even if it is, the typical load case is also not completely homogeneous. So we can use that knowledge to generate parts where we have different mechanical properties in different areas of the part, as shown in our vision on the right. And of course, we want to quantify the grain size. We want to use that. As a direct reference for the common single spot process without any defocusing, so with slower build rates. And of course, we want to investigate the effects of a heat treatment on the mechanical properties. So if any of you has an application in mind where this could be helpful, just contact us. We're eager to find out. But actually, why stop there? So if you have a multi-scanner system, you could also use those 2 or more lasers to actually do a synchronous motion during exposure. So you can have one spot that is doing the actual melting and another one with a different intensity distribution doing some other stuff around that. And if you're wondering what the perfect practical application for this could be, so are we. So we strongly believe that one of the key aspects in the future of additive manufacturing is to use that knowledge and that possibility to take more control over the actual melting process, not only for giving new properties to already existing materials, but also to create completely new ones. Thank you.